Good morning, ladies and gentlemen. My name is Gregory Murad Reis. I'm a professor in the Computer Science School. I'm also a researcher in the Institute of Environment. And today, AI is no longer a buzzword, right? A fancy buzzword, or a futuristic concept used in TV shows, books, and movies. It's part of our daily lives. It's present in our homes. It's everywhere right now. And it's reshaping the way humanity is interacting with the world in a very fast pace, faster than we can grasp and fully understand what it means. It can solve mathematical problems in a matter of seconds, complex ones. It can also propose solutions or even solve computational problems and analyze huge amounts of data that maybe 5 years ago, 10 years ago would be unrealistic to us. It's not only about coding and math, it's also artistic. AI is somewhat creative, and we can discuss that later on. It can produce music, images, just by giving a prompt, a script, it can produce images, videos. It can make Michael Jackson sing a Bad Bunny song. It can generate videos of avatars. I made one for myself, my digital twin. I presented it to my colleagues in any language, saying anything I want, in perfect accent. And it confuses us where the boundaries of creativity, human creativity, and computer precisions are. What are these boundaries? It also helps us explore the deep ocean, the space. It can help us cook better. It doesn't matter which field, AI is present right now, and it's our duty to fully understand it and use it responsibly. So, in a world dominated by uncertainty, can AI really augment our human capabilities? And this is one thing I keep wondering, and how? So what lies ahead? What comes next? Is it a scary future we're not ready for? Or are we in full control of what's gonna happen next? Who's taking the charge on this? So that's why we have this incredible panel here with these experts in AI, environmental policy, to explain the different AIs. There's not just one AI. What are the challenges? What are the limitations? What can we accomplish it? What can go wrong, but also what can go right with it? So what can we do to make it right? What can we do to be responsible in its use? Without further ado, let's start this panel discussion. Thank you very much. So, I'll start with Dr. Mark Finlayson. He is an eminent scholar, chaired associate professor of computer science. Dr. Mark Finlayson, thank you very much for being part of this panel. I would like to start with, as an expert in AI and natural language processing, could you give us an overview of AI and how we reached this level of intelligence? Is it truly intelligent? AI has been around for many, many decades. So why is it just a buzzword now?
A lot of questions in there. So I'll start with the easy ones first. Is it truly intelligent? The short answer is no. The long answer is, what do you mean by intelligence? So intelligence comes in many forms, many gradations, and there's certainly many things that AI can do today that we used to say, or we might even still say, that require intelligence. So an example I give in my class is that I ask the students if they think playing chess requires intelligence, and to play at the level of a grandmaster, does that require intelligence? And they say, most of them say yes, and that's a problem that was solved by artificial intelligence in the late 90s with the IBM Deep Blue system. And then I give another example. Does doing integral calculus require intelligence? And more hands usually go up, interestingly, in the class. And that's a problem that was actually solved in the 1960s by artificial intelligence. So one of the problems that the field has, actually, just as an aside, is that the target is always moving. So people will say, well, that task obviously requires intelligence. And then a computer scientist comes along and demonstrates an algorithm which will solve the task. And then people say, oh, actually, just kidding, that didn't actually require intelligence because now you've demonstrated how to solve the task. And so it's really this other thing that requires intelligence. So we have systems today that solve a number of tasks that could be said to require intelligence. Is it intelligent in the same way, to the same level as people? The answer to that would be no. I think there was another part of the question about how did we get here? Was that
Yes, how did we get?
Yeah, so AI is actually a lot older than most people realize. The term was coined in 1956. The first paper that's considered an AI paper came out in 1950. That was Alan Turing's paper on computing intelligence. And so that's what, 1950 to now, that's 74 years. So it's almost 75 years old, AI. Why is it only now really coming into the public consciousness? Well, again, there can be more or less subtle answers to that. So I was, over the pandemic, I rewatched and watched anew many old TV shows, one of which was The Twilight Zone. And in one of the 1957 episodes was an episode about artificial intelligence. So that's actually a really good example of what we would call sort of the first wave of interest in AI when it sort of entered into the public consciousness. There was another big wave in the 80s when the field was focused on a type of technology called expert systems. And that took sort of the business world by storm. There were 10,000 attendees a year at the Annual Association for Artificial Intelligence Conference. These systems were being created and fielded in factories and in the workforce, generally speaking. Then there was sort of what was called the AI winter, where the field sort of went through a dip in federal funding because it was seen to have sort of overstretched or overpromised and underdelivered. And now we seem to be back in another wave. And this wave, although for a lot of people it started last year with ChatGPT, in fact, I would really date it more about maybe 10 or 15 years ago with the advent of systems like Siri. So when the iPhone came out, we had Siri, and that's actually an AI system. So speech recognition is a very classic AI NLP problem, natural language processing problem. And that's when a lot of people started, thinking more about AI and the interest in sort of data science and big data. That's sort of an aspect of AI that has been going on now for 10 to 15 years. But really, I think the thing that really sort of walloped people in the jaw was obviously ChatGPT when it came out not last December, 2 Decembers ago now.
Yeah, so AI was present in universities and research, right? But when it reached the house of the citizens, right? Through Alexa, Siri, is that when people started paying attention? Oh, wait a minute, it's interacting with my kids. It's interacting with my family. So we started paying more attention to it.
Yeah, and it's also a matter of capability. So it seemed to have passed some sort of invisible boundary or border beyond which people are like, wow, this actually can do a lot of things that I didn't expect it to be able to do. Because it used to be you could talk with Siri, and so people didn't really think too much about the speech recognition aspects, and then you asked it a question, it would give you sort of a weird answer sourced from Google. But now ChatGPT can give you a very coherent answer, correct or not, that sounds like it comes from a person, right? So I think that blew a lot of people's minds, including, to be honest, a lot of researchers. Like I think a lot of researchers didn't think that the systems would be able to do that. That was very much a surprise to a lot of people who actually are experts in the technology.
Absolutely. Thank you very much. Yes, Dr. Annie Brett is an associate professor of law in the University of Florida. Her research focuses on environmental law, ocean, and coastal law. So, Dr. Annie Brett, thank you very much for being part of this panel. From your perspective on environmental law and regulation of emerging technologies, how are or should, right? It's a difficult question. Legal frameworks evolve to encourage the use of AI?
Yeah, so another tricky multi-part question, I guess, to start me off. How are systems evolving to incorporate AI? And I guess I'll answer this mostly from the environmental law perspective. Obviously, there's very different answers in different areas of law right now, fitting the many different kinds of AI that Mark was getting at. So in environmental law, I think how are systems evolving? The answer is, unsurprisingly, for the legal system, very slowly. And there's examples of this across the board. If you think about in oceans and coastal law, where I work a lot, we're thinking about autonomous vehicles that are operating underwater, which many of the people on this panel have worked on to some extent. And there are still basic questions like, are these autonomous vehicles going to be regulated as vessels? Like, is this a vessel or is it something else? So even the most basic legal questions haven't been answered yet. And answering them is unfortunately not a very quick process. So there's still multi-year international and national committees that are thinking about how we're going to answer these questions and figure out how to put new technology into existing regulatory frameworks. And it's not always simple, and there's a lot of barriers, even in relatively what we would think of as public good spaces like science, autonomous vessels on the ocean, right? Something that's collecting data and that has very little potential consequences. Even in those cases, the legal system is very slow. So the answer, at least for these physical systems, is it's slow. And obviously, there's very different answers when it comes to data processing and how that works in environmental data. And maybe we can talk about that a bit more later. But the how should they evolve? I mean, there's a lot of interesting work that's being done. I think it hasn't in the general space of AI regulation and how we think about how to allow innovation at the same time as we regulate it and create regulation that doesn't stifle that innovation. And that obviously is a very tricky balance, but it's not one that's new to AI, right? This has been an issue with emerging technologies for as long as we've had technology, is how do you regulate it in a way that allows innovation, but also prevents any potential consequences. I don't know that we've always been great at it, but there are case studies for if we think back to other types of technology, the internet, cars, right? There are many other ways that we've done this in the past, and I think AI, the ways that people are thinking about regulating it draw on those concepts, and they should. Like, we're thinking about regulatory sandboxes, other ways of creating kind of constrained regulation to still allow people to develop new systems while ensuring that potential consequences for the environment in particular are minimized.
Very good, thank you. And you mentioned the underwater robots. I have experience working with them, with these vessels, and there are still very few, if not right, any regulations on them. And we have here Dr. Ryan Smith. He's a professor and researcher in persistent and adaptive ocean sampling. So he's a specialist in underwater robots. And he's also the VP of Technology Solutions at OXA in Oxford, UK. So thank you very much, Dr. Ryan Smith.
Thanks for having me, Greg.
So Dr. Annie Brett mentioned the underwater vehicles, and I know you have a vast experience, right, all over the world working with them and regulations. So considering your research in this area, how present is AI right now in the development of these technologies in an industry perspective?
From an industry perspective, well, even from an academic perspective, it's, can you hear me? Is that better? Okay. I usually stand up and have a very projective voice. These things are really difficult for me. Those that know me know it's really odd for me to be sitting down. Anyway, it's really pervasive, and it's a technology that when I look at it and implementing it, either underwater in an ocean that's a little bit unregulated right now, which is nice, or on the public roads in Orlando, Florida, where I'm operating right now, which is highly regulated and highly observed and highly monitored. The one piece of AI is I think it's a huge breadth of space that's covered by one buzzword, but it's so diverse when you break it down. Just bringing back the history of it. It doesn't stem from one thing that we call AI, artificial intelligence. It's machine learning, it's Gaussian process, it's pattern recognition. It's a whole bunch of things layered on top of each other. And even when you layer machine learning models within machine learning models, you can actually create a lot of different spaces here. But we permeate it through. And the one thing that I say is AI, machine learning, whatever you want to delve into in this whole space, can be really, really helpful. But when it goes wrong, it can really, really go wrong.
Yeah.
And so you actually have this bifurcation that you really have to be aware of. And it works in spaces where we know what we expect. But in the places that we don't know what to expect, we have to be really careful. And I really like to go back to ChatGPT for a moment, because this engine is working really well. And I remember back in 2007, 2008, spinning up a Babel engine on my Linux box and trying to generate context-free grammar. And that was about the time when, I don't know if any of you remember this, but there was a computer science paper that was written. And it was written using the Babel engine, and it was context-free grammar, and it would produce fake plots and talk about these plots and do this. And they submitted it to a computer science conference, and it got accepted. Wow. And the whole presentation was about how they faked all the reviewer comments, how they faked the whole paper, and got it past the top people in the field in computer science to do this, and where things were at. And if you actually read the paper, knowing it was fake, it was pretty obvious. But if you didn't, the context-free grammar was so good, it just blew you away. And it was like reading, and going, oh, that kind of makes sense, but there's no content in it. And so when it was good, but if you didn't know about it, it could go really bad. So you could get these research papers published. Now with ChatGPT, my 11-year-old son found that when he was working on a history project. And it was really challenging to be able to try to teach my son how not to use things that automatically generated text that he was like, this is going to take me weeks, Dad. But in 30 seconds, I can get the whole thing done. Like, do you understand the productivity level that this just gave me? I really regret showing him that. Let's go back to how this permeates into robotics. As I said, it's deep, and it's vast. And I like to use this in different levels. So at the very beginning and the very end of the whole process of deploying an underwater vehicle or a robot, it's used quite heavily. So you want to start in simulation. You want to start looking at developing new algorithms, developing new technology in a safe playground, in a safe space. But you also want to test it to the extreme. So what you do is you can spin up generative AIs. You can create antagonistic scenarios, not agnostic, right? And you can challenge your system to the extent unimaginable by the human. And I say this because we have really vast simulators that we put our autonomous vehicles through, digital twins of any environment, and we throw all the scenarios at it, millions and millions a second. And I'll tell you what I can think about. The rainbow unicorn with titanium nail polish on its hooves and the purple tail, and I could go into more detail on that when it gets generated. But you'd never see that in public, and you'd never test against that edge case. But yet we do, because we have a generative AI that throws every scenario at it as you would. Then we can actually look at the controller on board, and we start to say, how do we get those new algorithms? How do we get that new tech onto the vehicle, whether it's an underwater vehicle or a car driving on the road? And you look at low-level controllers, low-level systems like that, and in most cases, and I really believe this, physics still works. They did that really good many years ago, figured out physics and closed-form equations. I love your integral calculus, Mark. I'm going to keep coming back to you there, because when you have an algorithm, when you can solve it when it's closed form, don't substitute. Like, that just works. You can write it down. That's why we still teach it. That's why it's still there. But when you have those ones that you need the computational power to solve, there isn't a closed form equation, you should sprinkle a little bit of the AI, a little bit of that on your physics cupcake to make it all the more better and tasty, right? That's where it has the power. And so you get into model predictive controllers, you get into behavior-based controllers that are fundamentally rooted in physics. They work really well, but then they can adapt as they learn and see different scenarios, and they can become a little bit better just by adding that extra little term that we don't think of, that in underwater is a drag term. How you're accomplishing moving through currents that are unreliable, that are time and space varying, and things like this. They can adapt to that and modify their controller on board, and that's where you gain the power. And then you can move through to your perception. And we have really good models in perception now with ML-based techniques. And so you can sprinkle that through. And so as you come through gathering data, looking at it, you can very quickly on the new GPUs with some really smart intelligence process huge amounts of data very quickly. So your edge processing becomes viable now. What we used to do early 2000s, have these vehicles that were out in the ocean for months at a time. And we used to have them sit on the surface for like 30 minutes on an Iridium modem, spending about $2,000 a month on a cell phone bill per vehicle. It was absolutely crazy to get some data off of them that we could then look at overnight, right? To then the next day hopefully catch them to say, this is the updated state of the situation. We can actually do on board on the compute, which is, honestly, we use a cell phone inside for most of the computes on these things, because they've got an IMU in them, they've got a camera in them, they've got some good processing in them, right? And they're pretty darn cheap these days. And you can
I
throw
use
those
them
in.
too, yeah.
Yeah.
In my own robot.
So you can actually access edge node computing with super advanced tech that even 10, 15 years ago had to be done on a desktop in your office. And so that permeates through the perception. And now you actually go into runtime. And you can, with the edge node processing, you can sprinkle some in here and say, what's happening in real time? How do I have to adopt my object detection or my object classification on board in real time when I've got a vehicle driving on the highway, experiencing new and different things all the time? We use it where I am now, specifically in giving the vehicle an examination to get onto the road. So our autonomy system sold with insurance to say this vehicle is insured and assured to be able to drive in a certain operational design domain. It's been tested against all possible scenarios and edge cases for a certain area. And the vehicle all the time is looking at scenarios and saying, have I experienced this scenario? And if it hasn't, it calls for help and says, hey, I haven't been tested against this. I don't know if I'm safe or not. Can you help me out? And the vehicle has that intelligence on board. And it's only enabled through a little bit of AI blending here, I'll call it, because I don't want to go into the details of parsing that through. But you can imagine, how many of you in here are pilots? Excellent, you'll agree with me here. What do you fly?
I used to fly Navy jets.
Navy jets, okay. We're going to have a great conversation. I've got a Beechcraft Bonanza V-tail, 1972. I can definitely assure you that I can fly that plane. But if you take me into F-14? S3 Viking. If you sat me in the cockpit of that, I'd look around and go, yep, this is an airplane. Definitely. I am definitely not certified to fly this airplane. That's what our cars do, because really what you want to only operate what you're tested against, right? And I should not jump into a 777 and try to fly a few hundred passengers transcontinental, right? I'm definitely not certified for that. I wasn't tested for it. So you can actually develop systems that can classify your environment, the scenarios you're seeing through cameras, lasers, radars, and say, what does that look like? What's the feature vector that defines the scenario that I'm seeing? And have I been tested against that? Or how far away from the examination am I to be able to say, I might be operating in an unknown, unsafe situation? And so even at runtime, we apply a lot of these techniques to be able to define how the vehicle should decide if it's safe. And that's a paramount when you're operating AVs on the road. Now afterwards, is this long enough, Greg? Enough detail? So then afterwards, I just needed a breath there. I hadn't taken a breath for like 7 minutes now. So afterwards, you can only imagine how much data comes off of these things, even if they're underwater vehicles out roaming around for a few months, or if it's a autonomous vehicle driving on the road. You know, there's terabytes of data a day that you need to roam through and look at. And I don't know about you, we were talking about large traffic this morning on the road and different scenarios, but I'll bet for every one of you driving around, 98% of what you see on the road, you've seen every single day. You've seen it so many times. It's not novel, it's not new, it's not interesting. So how do you run through all of that data and then pull out those couple of scenarios, those 10-second clips out of tens of hours of driving across multiple vehicles every single day to say these are the instances that are new, that are novel, that we can learn from? And afterwards, that's where we go in and dig, and that's where we pull out the cases that can advance our system that little bit every single day without having to spend human time looking through everything and bringing it along. So that's about how we use it I see it from end to end in developing an autonomy system for a robot.
Thank you very much. And you mentioned the data. I want to get to the data, sharing data, and how dangerous these can be, and also the simulations that you mentioned. We have a specialist in simulation and modeling here, Dr. Jason Liu. He is an endowed C computer science professor and director of the School of Computing and Information Sciences here at FIU. Thank you very much for being part of this panel. It's also interesting the use of AI in simulations and creating all these different scenarios, right? And there's also a distinction between being able to create AI tools and able to use them, right? There are two distinct, people may claim they know AI in the sense that they just use the tools, right? We don't even know if they use it responsibly, but there's also the other side of the coin here is creating these technologies, right? And as the director of the computer science school here at FIU, how do you see that evolving in the academic scenario here?
Yes, thank you, Greg. So as a school of computer science, I think the one I would like to say is, we are a large school. We have a school of actually 4,500 students. And they are actually into several areas: computer science, information technology, cybersecurity, data science, and artificial intelligence. So people will ask, what is actually computer science? My brother actually interpreted computer science as, Jason, just come over and fix my computer. And my neighbor would say, help me hook up the Wi-Fi. We have good neighbors. And but really, if you think about computer science, there are actually three components to the computer science, right? So there is computation. What is computation? This is computation. The devices, computer systems, computer architectures. This is computation. Your Siri on your countertop is actually a computer system, right? It's just to have a magnified sort of speaker and microphone. And so computation is really, really sort of how to make a computer systems efficient and energy efficient and fast and respond to the task that you want that system to be, right? So the other aspect would be algorithms, right? So you look at computer science, and artificial intelligence is an algorithm, right? So or not one algorithm, it's a lot of algorithms, different kind of machine learning tools and deep learning. These are sort of algorithms and models actually created by computer scientists, right? And the third part is actually very important, actually really relevant to this workshop. It's data, and you have to have the data. And where the computer, the AI systems, why we are experiencing the winter AI that Mark actually referred to earlier. It's the data was not there yet, or at least not incorporated into the system that you want. And also the computation was not there. You are not really having those supercomputers that are able to train on the data, be able to provide something like called GPT, right? So these are actually really three components of computer science, and a lot of researchers and students actually learn about computer science techniques are actually getting into these areas. And if you think about that if we talk about AI in general, these are the actually three components that actually the three important pillars for AI, right? Computation, data, and algorithms, right? And now, when you talk about what computer science, and as a school, that what we do with respect to sort of AI, there are actually three. I can think from the education aspect, there are three different things that we do, right? We are proposing for a Bachelor of Science degree in artificial intelligence and data science, and that's actually trying to sort of educate our students to be ready for AI and data science. This is very important to actually the foundational knowledge, how to deal with this. The other aspect would be sort of help the students at the university to be what I call it AI, sort of literate or AI competent, right? So that would be something like the micro credentials, some kind of embedded into core curriculum to help our students to be able to handle these new technologies. And the third part in terms of education would be what I call it with respect to AI would be AI plus X, right? So we have so many areas, just like the early days of computer science, when computer comes and people think, what are we going to do with this box? Right? The same thing is that what we're going to do with AI. How do we actually be able to utilize AI in different areas? In this particular context, it would be climate, environmental science, and these areas can we actually be able to create this AI plus climate science or climate science plus AI, right? Have various different kind of combinations, have our students to be able to use the tool and be able to cope and solve problems in that case. So long story short, I think that education aspects, that being a school, we can play a very important role there. The other side will be the research. That's where I have 60 plus faculty members and doing research in different areas, and be that algorithms, be that computation systems, be that trying to data processing, database. And all these areas, or cybersecurity in that case, and because privacy and security would be very important. And we have actually new areas developed, like AI fairness and trustworthy AI. We have a new project, actually, Expand AI project. It's $2.8 million with my dear colleagues in the Institute of Environment. And we're dealing with is actually trying to create this modeling and data center and help with the data in that sense. Also actually be able to make the data ready for doing research, how to actually apply the AI models and use AI models based on the data, right? So these are the kind of research areas actually sort of blossoming. I've seen my colleagues actually in computer science and being able to collaborate with various domains and applying AI techniques in this context. There are a lot of fruits to be picked at this point, because suddenly the capabilities, I think that the early discussion we had, suddenly there are a lot of capabilities that was seen before. Was like, well, people have done this for 50 years. And suddenly now it's saying, oh, you know what, the system is ready for that. We have the data for that. Can we actually apply the model and combine with the AI techniques and be able to create more efficient, more trustworthy AI or technologies and actually be able to solve those problems?
Thank you. Yeah, the privacy is a concern as well. We're going to get to that. Now I would like to introduce Dr. Michael Sukop. He's a professor in Earth and Environment, also hydrologist and specialist in coastal resilience. He has a coastal subsurface monitoring project right now, and he prepared a magnificent presentation for us for more applications of AI in this domain. So thank you very much, Dr. Sukop, for being part of this panel.
Most welcome, and thank you for having me again. And I prepared the presentation because I need props. I can't be extemporaneous like these folks. So anyway, I'm going to speak mostly about this new coastal subsurface monitoring program. It ties into the coastal resilience theme here. But I'll touch briefly, super briefly, on AI and environmental data, and then get onto the coastal resilience part. So just as a kind of a plug almost, I still like keeping my hands in some programming, and so I've kind of discovered Google Colabs, and if anybody still likes to program, and I feel like it's an indulgence for me. I'm happy to work with students and still do some of that. So it's amazing because it really can help you code. On the flip side, I'm still glad that I learned programming on punched cards, a long time ago. Okay, and then machine learning-wise, and I hope you can see a little bit of this. It's kind of we're looking at years across the bottom of these time series axes here, from I think about oh gosh, I can't read them from here, so I don't know. But tens of years at least, and a training period in the beginning, and then a verification period at the end. And these are water levels in monitoring wells around Miami-Dade County. And so this is an important problem for us because we get flooding when the water table comes to the surface, and there's also saltwater intrusion that's controlled by these water levels and so forth. So we're very interested in predicting these things as much as possible. And as we were talking about physics models here, the blue stuff is the actual observations. The green stuff is the physics-based models that are very difficult to use. It's a multi-million-dollar model developed by the United States Geological Survey, and it's very challenging to operate. And then you have the machine learning model in orange, which basically captures a lot of the variability, not perfectly in many cases, but it's a pretty straightforward thing to go. Now, like the comments we've been hearing, if you get stuff that's out of the sample space, the machine learning model isn't going to know what to do with it, basically. So as sea levels continue to rise and so forth, it's going to be very problematic for these models to keep up because it's not something that's in the database in the past, right? So, and finally, I guess on the far side, you can see the size of the dots there represents the errors. And so the bottom one is the physics-based model, and the upper one is the machine learning-based model. And so it basically does better in reducing the error. And this is the simplest type of machine learning model. We're only looking at the individual time series from these wells, individual wells, and we don't even take into account the spatial correlations and so forth that are relevant in this case. And so I had the pleasure, I'm part of this environmental finance and risk management program here. I had the pleasure of teaching the first time this environmental data analysis for environmental finance last fall. We had a cohort of maybe 7-ish or something like that. And it was quite interesting. You know, we had a lot of lofty goals of things to do with them, but what my finding was basically is that they still need basically basic probabilistic knowledge and statistical knowledge to really, before they can go on to much higher level types of things here. But it was an interesting experience, and I look forward to growing in it too. I put part of the blame for not making as much a connection to the finance stuff on myself, because I'm just starting to get integrated to this a little bit and learning about it myself. So. Okay, so now onto this coastal resilience thing. You can't even read this either, but these are a bunch of different papers that have come out just in the last, many of them are from just less than a year old, but looking at what's happening in the coastal subsurface near cities, basically, and the challenges that saltwater intrusion near the coast and tides going up and down and kind of being propagated inland create for foundations and other buried infrastructure that's so important in our heavily developed coastal areas. And so this really was motivated by the collapse of the Surfside Tower, and this could be a video, but I don't think I have any control over that here. So, and many people have seen it before, but as soon as this Surfside Tower collapsed, we realized that there was no data available basically in the subsurface where that tower was. And so that left a lot of unanswered questions about what might have happened. A lot of people are looking at it still. But so let's see, episodic submergence and so forth. I'm going to skip through some of this. Let's see. Had a lot of corrosion there, and when it was all over, it looked like this. The ocean is shown in the background there. So we worked with Wasserman Schultz's office through our governmental relations people. And in the end, we can't read that either, but we got to, here it says 11 million. We ended up with about $9.75 million to address this problem in the region. This is kind of a schematic. You can see on the left side the freshwater, and then the darker bluish is the saltwater in the groundwater. And so we have the barrier islands there, and the ocean drives everything. Sea level rise is important, and also the tidal fluctuations, storm surge, and so forth. They propagate inland and into the groundwater system. And we have these freshwater lenses, which are very important in the barrier islands. And what I'm showing there is the foundations of the buildings. A lot of times are concrete encased, or sorry, the other way around, steel rebar encased in concrete. And if that's not done well, then those things can deteriorate and create risks for buildings, and certainly pipes and other types of subsurface infrastructure can be affected. And on the far side, we have the far left side, we have the drinking water wells, which we all rely on here. Any water you get in Miami is coming from the Biscayne Aquifer, basically right at the surface. And so we have some models. This is a saltwater intrusion model for all of Miami-Dade County, and it's a zoom in to Surfside. You can see things, as the days pass by, the interfaces change. We got the blue being the freshwater and the greenish being the saltwater in the subsurface. You can see this moving a little bit as the water table changes and so forth. But this is an extremely poor representation of what's going on in the barrier islands because of the lack of resolution here. So these are 500-meter grid spacings, and they really don't capture what we expect it to look like under the barrier islands. It does a really good job at the major saltwater interface that protects the drinking water wells, and that actually was the model's principal purpose at the time, and still is used for that. But we don't. Again, it doesn't address the stuff that's going on where a lot of the heavy development is. And similarly, we have probably one of the best groundwater, saltwater intrusion monitoring networks in the world here in Southeast Florida. And these are the wells, and they look like it's quite dense in terms of the whole region. But then if you look in, and it's going to be very difficult, but there's a handful of points here, 4 or 5 points that create these two lines on the far left that show where somebody estimates the saltwater intrusion is, down deep anyway, based on just a handful of points. So, even though it looks pretty dense, it really isn't, and it doesn't provide much control. Plus, we know nothing about what's going on in the barrier islands. So our plan is to put in these coastal subsurface monitoring system stations, quite a few of them. I think 80 is about the total number. Big focus on corrosion parameters, pH and salinity, and various other things in the subsurface, sulfide and so forth. This is just an example. We were thinking about doing paired systems. This is Hallover Park and our Biscayne Bay campus up north. But most of them would actually be, well, here's another transect to show what this looks like, and there's Hallandale Beach. I can't quite make out the transect here, but there's little yellow circles or ovals that show the progression of the monitoring stations going out across the island from the beach. But, they'd look like this. It's just kind of a solar panel and some protective things around them. And we want to work in these really challenging environments, heavily developed urban environments. And that's why it's so expensive, frankly, because we have to get access to property and permits to put things in. Plus, we expect the subsurface to be very congested in these areas with a lot of utilities. So that's one of the big challenges. Thank you.
Thank you very much. So, Dr. Annie Brett, we've been talking a lot about the data, either the lack of it or the big data, right? So there's also something about sharing data. Some agencies are allowed, some researchers are not allowed to share data and validate them. Are they truly real data, or are they just generated? So regarding ocean and coastal law, what are the trends, the challenge, and the limitations you find in the shared data environment right now?
Yeah, so I think we've heard from all of the panelists how important data is for all of this new technology and new AI technology in particular. Without baseline data, we have no idea what's happening in the environment. We can't create any of these systems, and there's still huge data gaps, right? Even in Miami, where we have relatively good data about a lot of the climate impacts that are happening, it's still very spotty, and most places are not nearly as good as it is here. So huge needs for data, and right now most of the environmental data that we collect, right, is driven by the government. So NOAA, for instance, the National Oceanic and Atmospheric Administration, collects over 80% of the world's data on the oceans, which is just a staggering number. So that is all US government-funded data that's being collected. So as an actor, the government is extremely important in driving data policies and data sharing and all of these different pieces. Unfortunately, the government is slow to act, and a lot of the ways that this data was regulated and is required to be collected are a bit out of touch with what we currently need for AI systems. So agencies, even within their own agencies, are not sharing data. So within NOAA, you have data that's collected by scientific equipment that goes to one specific piece or one specific office. You have other data that's coming in from fishing vessels, for instance, on how much fish they're catching, also under the NOAA umbrella. But instead of being shared and some central repository, it stays within the fisheries office. And so you don't have any interchange. And the fisheries data actually is still, in a lot of cases, coming in on hard drives that are being mailed into NOAA, right, which is the same policy that was in the 1990s. And it's the same policy because there's a specific NOAA rule, right, that says that this is how you send data to us. And those things haven't been updated. So there are these systems that are historical relics at this point that really prevent a lot of what we need at this point for having accessible, open, shared data within government agencies. And that's hindering probably some progress, though there's a lot of new efforts that are being done through these agencies to try and modernize this. So NOAA has been working with a number of different large cloud providers to try and store their data, and there's actually some really interesting public-private partnerships that are coming out of that, where Amazon has essentially agreed to host NOAA's data for free, which is great for the agency. And in return, it's much faster for processing that's happening for private users that might be looking for weather data and things like that. So some interesting new partnerships that are pointing to how this can be done. But I think that there's clearly a need for data, and there's a lot of drive for more environmental data. But there's also a idea, I think, that open data and transparency is inherently an unalloyed good, which I think is true in a lot of ways. But there is this idea right now that if we get more environmental data and we make it accessible, it will inherently be used and used in ways that are positive. And I don't know that that's always the way that things work. And certainly the data that's been legally mandated in a lot of cases is simply not shared. But even when it is, many of you are familiar with NEPA, other types of regulatory programs that require different data. That data maybe is becoming more accessible, but even when it does, it doesn't really lead to major changes in activities. So there needs to be, I think, more consideration of what then, once we share this data, once we make it transparent, what do we want it to do? And right now, transparency for transparency's sake can be very resource intensive. And so where we need to focus our efforts, I think, is a really important question to ask going forward. And some of these scientific purposes are really great, but others, I mean, there's, in the climate context in particular, right, the people that are gonna be able to use the data most effectively are the well-resourced insurance companies and other development companies, and not the people that are going to be impacted because their home is flooding, right? Because they own a single-family home somewhere in Miami. So the ways that data is made accessible, it's great, but it still requires a lot of expertise to be able to make use of. And so transparency will get us some direction, but it's not going to help a lot of the people that are actually being impacted. And so how we figure that out is something I think the legal system has some answers for, but it's probably not going to be the place that we need to actually look to for some resolution and some innovative thinking about how to accomplish data sharing in a more effective way.
Can I just add to what you're saying there in the sense, you put a lot of complexities and challenges around data sharing within the United States, within agencies within the United States, and how we look at those, what different agencies have different regulations and what can be shared, what pieces, and in what data formats. What's the next layer when you look at international? And I know this from a couple of different contexts which are outside of the environmental space, but there's GDPR regulations that exist across international boundaries that restrict us on sharing different types of data that are collected with, on land-based platforms and things like this, which may permeate. And one of the main ones with AI, I'll take a little tangent, then I'll let you jump in here, is that there are certain countries that don't allow the clear showing of faces and images to be transferred with data, so you have to blur the faces, and you have to blur some recognizable marks. I don't know if much of you realize, though, that by doing that and sharing the data, it actually makes it unusable to train any machine learning algorithms to identify humans. And so there's a piece that we're losing. There's a depth of the data that's being erased because of a data sharing across boundaries. And where that data gets stored and housed, I mean, Google and Amazon are worldwide. People are getting around this by putting data in different Google repositories in different countries to not have to follow these guidelines and regulations, which is a good and a bad thing. And I want to know what your view is on international data sharing and how that makes things a heck of a lot more complex, because that's a nonlinear complexity that I just put in.
Yeah, so it is. So if the US is a complicated system, obviously you add in every country which has its own complicated system, and it becomes exponentially more complicated. And the international picture is very interesting because the US has been relatively slow to act in terms of regulating AI and all of this. So while our regulatory picture is complicated, it's not nearly as complicated as places that have put AI regulation into place, or data regulation more broadly, like GDPR. So working with that is very, very difficult, and I think it does disincentivize a lot of different types of data sharing with very different conceptions of privacy and all that. I think with environmental data specifically, it's a little bit less thorny than it is with some other issues, right? Because typically we're looking at water quality and not necessarily people's faces. So the scientific agencies globally have been relatively good about working with each other to try and come up with, let's call them standards, and they've been working on these standards for 30 years, so it's not like there's full agreement on what those look like, but it's a little bit better if we think specifically about the environmental context as opposed to others. But the international picture in general is very thorny. I think there's some interesting ideas about how to deal with that, like federated networks and things like that, where you can have data stored in various different places, and then the way that it's shared and extracted can be context dependent in the sense of complying with specific countries' regulations. But I will say that it's an extremely complicated system, and there's not any really good answers, right, about how it's done. Generally speaking, it's a little bit better when it comes to physical geographical data than it is with other things, but it's still, and this is particularly true because like in the US where the government is the one that's generating most environmental data, that's true other places as well, and some governments are more willing to share, some are less, and everyone has different data formats. So I don't know that there's anyone that's really solved this problem, but there are a lot of international coalitions that are working on standardizing things and coming up with new regulations, but I think this will be an ongoing conversation for the next 50 plus years, right, is how we do this well. It's not happening quickly.
Yeah. And my
I'm
last
really glad
question
you got
here.
that, though.
True. Dr. Mark Finlayson, so AI can be used to generate and spread misinformation or maybe good information. So one last word on how can we use it responsibly to communicate climate change narratives more effectively and to a broader audience? How do you see the role of AI in this right now to reach a larger audience?
Microphone here. I think there's kind of two aspects to that question. So, there's a lot of worry about using these generative AI systems to generate essentially fake news or biased news, or biased even scientific articles. I think that is a problem. It really, I don't think the fix is really technological. I think it's more of a policy, social problem. So there needs to be we need to raise awareness of these issues in the general population. We need to improve people's sort of savviness with regards to news and information consumption. The reputation of channels is very important to ensuring that you're getting good quality information. So part of that reputation is ensuring that there are humans in the loop, where even if AI is being used to generate some of the text or some of the information, that it's being checked and vetted by people. On the technological fixes side, I'm actually involved in some programs funded by the Department of Defense, which are looking at ways of using AI to detect when people are trying to conduct malicious influence operations. These are mostly in foreign contexts, in the context of things like Russia and Ukraine or China, foreign countries that are trying to manipulate either populations in countries that they're nearby, or possibly the militaries that they're in conflict with. So I think there's a lot of potential for AI to be used in detection of when this is happening. And so that can be used to either, take down sites or respond with counter narratives, or just point out to people like, hey, this is made up information that's coming from this source. Often just pointing out the source of information is a very powerful way of guarding people against it, because whether or not something is persuasive depends a lot on who it's coming from. And if you think it's coming from one source and then you realize it's actually coming from this other source, possibly a source you don't necessarily trust very much, that's a very powerful way of making people put up their guard. So yeah, I think AI is both part of the solution and part of the problem and part of the solution for that.
Thank you. Thank you very much to the panelists. Now I'm going to ask the audience if you have any questions. Anyone would like to start? Silvio?
Hi, morning. Thanks for this great panel. My question is really about kind of geospatial data and how sort of the interoperability of maybe some flat data. Hey, thank you so much. Some of the interoperability between, kind of 2D data versus 3D data comes into the mix. And I've been trying to figure out that interoperability between databases. I mean, just within Miami, much less more, multiple government agencies. The concept of data cubes has come up as a way to be able to analyze or store 3D data, which will help us create better volumetric calculations for environmental ecosystem services and things like that. So, by their nature, are kind of 3D. I don't know. I haven't really heard anybody mention that or how to solve that issue. Is anyone thinking about that or working on that right now? Thanks.
Okay. I think that on one side is we're talking about the data management and how to actually be able to manage data from different sources, and the format and also the legal sort of implications are part of the sort of the stumbling stones that it's sort of impeding some of these sort of a free use of the data. And there are mechanisms that are computer systems that actually be able to allow the data to sort of incorporate data and merge data and actually use, some of the projects that we're actually embarking on, actually trying to sort of create this sort of a data management system, and so that we can actually be able to use the data from different sources and be able to do discovery, right, do science. Now, I just want to sort of extend this a little bit more on the question here. I think when we actually talk about data, you think about environmental science or climate research. I think this is the area is both sort of a data rich and data poor. So it's from the rich aspect, and I think I mentioned 80% of the data that NOVA has, ocean data. It's a lot of satellite, the sensor networks, and at FIU we do autonomous vehicles and actually roaming around and collecting the data. And for the data that and the buoys and so on and so forth, and that data is actually coming in, and some of the data would come in real time, and enable some of these the models to actually be able to drive these models to actually doing predictions, forecast, and analysis. And on the other hand, it's data poor, and that means that not every point of the surface actually being collected at every depth, right? So you only have a few stations there, how to interpolate the data so that actually be able to be of use. And associated with that, and then just expanding the question here, and there are embedded biases right there, right? So when we talk about AI, I think Mark can mention this more. There are biases actually to how fair the data that you can use, right? And what are the ethical implications? Because the data would be generated in rich countries may not be available for poor countries, right?
Or not applicable.
Right, exactly. And on that, for example, just for environment, if you have a model actually running based on data on the Gulf region or North Atlantic, can you apply that actually right here? So that these are actually really interesting research questions and driven by data. And I think that's a sort of the broader than just sort of trying to merge the data from different sources. And that's a sort of more of a mechanical aspect. Yes, there are systems that actually need to be developed for that, but there are a lot more in terms of how to actually incorporate the data, remove the biases, and hopefully be able to make the models more useful.
Paulo? Yes.
So for environmental monitoring, and our primary goal is to predict and prevent potentially harmful events in coastal regions such as Biscayne Bay. But sometimes we are so focused on the technicalities of our algorithms that we lose track of the broader impact on our community. So my question is, from your perspectives, how can we all collaborate to minimize this gap between what we develop in our labs and the strategies to really make the difference in monitoring these environments?
I can speak to this. So I think that the answer is one that most people don't end up doing because it's time intensive, which is that you actually need to go out and figure out who the people that are going to be potentially using this information or this technology are. So who are the managers that are going to take this? I don't know if it's harmful storms or what specifically you're looking at, but who are those individuals, and talk with them about what they actually need, because what information can be put into our regulatory system in terms of information that can be used from a legal perspective or from a management perspective is often not what we're getting from scientists. And I think that's the fundamental disconnect. And those conversations need to happen very early in the process of creating these projects, and they usually don't. And they usually don't because it's effort on the side of both the scientists and the policymakers to actually work together on these projects from the get-go. But if you don't work together early on, by the time a product is created, it's essentially the technical details have been worked out. You've already developed a thing, and you've probably written some papers about it. But what you've created may not be usable anymore. And if you do this early on, you can make several tweaks, right, to the project so that what you're putting out is a data product or a type of program, whatever it is, that's actually going to be something that can be directly input into the management process. But so I think it's very doable to do that, but it really just requires conversations between scientists and managers earlier in the process than are currently happening, I think.
I think Alfredo also.
Yes, thank you so much for all the ideas shared today. I would like to put together these two ideas in my question about AI being popular because people can use it, and also using AI in the industry. So how are you incorporating this idea of sharing like these AI strategies to make things like more popular into people? So for example, Professor Smith, Dr. Smith shared that he uses AI to come up with scenarios in which the autonomous vehicle moves. So how do you like this idea of making this available to the people so that you come up with more scenarios that you can possibly imagine? Thank you.
It's really interesting you say that because there's a lot of what we do that we use the AI to help us understand and improve the autonomy. But there's quite a bit of it that we do want to show our customers, we do want to show who we're bringing it to show what the edge cases are. There's also some of it that goes kind of silly, that we do test those edge cases that you show in a joke on a slide in a PowerPoint and you laugh about it and move on, but there are many of those that you kind of just go, it went a little bit funny there. It put 5 lanes and a bicycler driving backwards with a pink helmet on, and then there's a dragon that's sitting over there in the corner, and you probably don't want to show that piece of it. But there are a lot of edge cases that we can do that in the generative AI space and in that AI space that we put forward and say, this is really important. One concrete example I think I'll nail down is we were working at a oil refinery, or a natural gas refinery, and doing some autonomy for some monitoring around that. And our generative AI was running through some scenarios and came up with the fact that there was a large box at a T-junction, that's what they called them in the UK, T-junctions. It's a 3-way stop, basically. I'll translate back and forth. It's found out that if the car was traveling at the speed limit on the refinery of 15 miles an hour and somebody walked out from behind that box that was there at the stop sign, there was no stop sign for one way, that the vehicle would actually hit them. And that had nothing to do with autonomy at all. It was the fact that the speed limit was incorrect for the operational procedure on that site. And we went back and we said, hey, we think there's an issue here. We found this edge case of a vehicle comes up going 15 miles an hour, and if a person walks out from behind this big box that happened to be there, there's a big transformer actually, you're going to have a problem. And the head of the site went, God, I've had 4 of those in the last 7 months. And then said, yeah.
Not anything about it.
Yeah. Well, he said he didn't know what to do about it. And I said, well, if you make the speed limit 12 miles an hour, you won't hit them. So they changed the speed limit to 12 miles an hour. I got a call about 7 months ago. I said, 2 years ago when you told me to change the speed limit, haven't had any incidences in the last 2 years. And it's not the fact of looking at it, it's stuff that you just don't know. Why is the speed limit 15 and not 12? It's because we don't have speed limits on the highway of 72 miles an hour. We have them 70 or 70. We just like 0s and 5s for some reason. And it's not anything based upon the safety or the consideration of other things. This is what we found out empirically, and that was driven by AI. So we want to share those things. I think that's a good one, Alfredo, of just saying, what are the pieces? How can we enable? How can we change safety? How can we look at this and enhance the society while sometimes getting some silly results on the side that we just might want to chuck in the bin. That's the trash can, by the way, the bin.
Professor Obey?
Yeah, thank you. A little different question.
The microphone.
I'm with Institute of Environment here. So I'm not an AI expert, so I'm trying to hang out with some AI folks.
Either are we. It's totally fine.
Yeah. So this question, when I was a graduate student, the big thing was what we call stochastic differential equations, trying to bring physics into stochastic processes. And if you're working on one of those topics, you're a cool graduate student. And so I was curious the state of science in AI merging or converging physics with stochastic processes, because I know we are working on physics-informed AI. Jason, we have that project from NSF. But I was curious the state of science on merging, AI machine learning technique with stochastic processes so we can bring, like the compound flooding problems that we are going to be working on. I was curious if you can comment on the state of science on that.
Me? You go first. So you're asking about the combination of stochastic techniques and artificial intelligence? I'm sure there's someone doing it. My specialty is natural language processing, so that's not an area I'm all that familiar with. I mean, I think people are experimenting a lot with trying to graft AI, and especially generative AI, onto a lot of pre-existing techniques. One notable weakness of the generative AI systems is mathematics. So it's very hard for them to do precise mathematics or sort of logical reasoning. And so I think there's a lot of interest in trying to leverage the power of these systems to explore large spaces of possibilities in sort of a statistically robust way, and marrying that with the strengths of other techniques. So that's the best I can do.
I'll give you an example I looked at a few years ago that's actually becoming tractable at the moment. I worked with, back in late 2000s, worked with JPL on building up the ROMS model for Southern California in the Pacific Basin. So an ocean model, nested grid ocean model that, pretty stochastic process if you look at that, and solving it. There was also the HOPS model, which is the Harvard Ocean Prediction System that was on the Atlantic side, and having put robots in many different parts, all the oceans around this world, you were always looking for some kind of model to give you some kind of idea of some currents that were going along. When I was in Australia, we worked on developing one for the bays and the huge tidal fluxes and things like this that were not well done by larger ocean models. So back before, I always thought that, God, there's some really smart people that develop these really great models. If I could take the best things out of them and put them into a specific place at a specific time, it would be a really good thing. And you could find the outliers and things like that. The processing was not available now. In the last year, I've started looking back at the problem, and it's tractable at this point. And so you can actually take a mixed version of the models, combine them together, and actually have a much better prediction based on several different models that are having several different outcomes over a stochastic process to be able to predict what's going to happen in that part of the ocean with models that weren't trained there. To give you a concrete piece.
So maybe I'll just add to that. So my background is actually in discrete event simulation modeling, and throughout has been sort of working on sort of combining, different kind of models, including the stochastic models and with discrete models. So I learned when I was in my grad school, and the first thing we learned, all models are wrong, and some models are useful. So that's basically the kind of the kind of a baseline where you draw. So basically, for AI models that can solve specific problems, that a lot of techniques actually being developed using sort of embedding AI models, replacing some of those computationally kind of very expensive models in some of the scenarios. There are different techniques actually being developed over the years, and I can't enumerate them all. Being a student, you're a student forever, and to learn about all those kind of model, exciting papers to read. I think AI is definitely a very, very interesting tool. It's actually apply because it can actually discover those kind of hidden functions that is very difficult to describe. And so that actually impose a lot of very interesting kind of applications, like in this particular case, and how to actually combine those models, and replacing those models actually can give you better forecast, better prediction, at the same time, computationally efficient, right? So it's a model that actually can be neural network and actually can be able to use in those kind of scenarios and give you a good prediction. I think it's just the research in this area. That's why we have that project. But the research in this area is really exciting. So these are the kind of opportunities that actually brought around by all these newly developed AI techniques that in this area.
Thank you. Please, the microphone. Yeah. 30.
I'll try to be quick. So at first I was thinking about the difference between AI and a super, super, super duper computer, and what the difference is. And it seems from some of the comments they were a little bit synonymous. And so my question started off in the national security sense regarding like non-attribution, cyber warfare. No one knows where anything's coming from anymore. But the question between the insertion of bias or motive versus self-generated bias or motive, and how that would play out. And we can bring it down to environmental policy if you would like. But that's my question.
So the first thing I want to say is, let me try to clarify that distinction between just a super duper computer and AI. So one of the examples I use in class is, so the amount of video that's uploaded to YouTube, there's something on the order of 31 years of video uploaded every day to YouTube. Wow. 31 years. So in the 3 days of this workshop, there will have been more video uploaded to YouTube than any individual in this room will be able to watch in their entire lifetime. Now, that sounds like a lot, right? A lot. Keep in mind that all that data is being generated mostly by people. I mean, there's some sort of automated devices doing it, but those devices were built and installed and live on planet Earth, and so they're sort of limited in a certain degree. Now, if you look at a problem that requires intelligence to solve, so let's just take a simple example of chess, and you compute what are the number of possible chess games that in a 40-ply game, which is or 80-ply game, a 40-move game. If you compute it out and just kind of estimate, okay, you have 5 possible moves per turn, and this X number of pieces, and blah 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 blah, you will get more possible games than there are atoms in the observable universe. In fact, by a large margin. So even if every atom in the observable universe, you could write a full chess game down on it, you would run out of atoms long before you ran out of chess games. So that's the difference in scale between just big problems, super duper computer problems, and AI problems. And so, exhaustive, super duper computers are great at doing exhaustive solutions to certain things, but not, it's just too big of a problem to do exhaustive solution, to look exhaustively for the solution. So that's why, and the amazing thing is, a lot of these problems like vision and audition, locomotion, a lot of the problems that people solve unconsciously on a daily basis are also of that sort of size of the universe order of magnitude. So, but we solve them almost effortlessly, right? So there's something about how, intelligence solves those problems, which takes these ginormous problems and simplifies them down into a way that we can solve them with, 20 watts of power almost instantaneously. So that's the first thing I'd say about the difference between just a big computer and AI. Going in terms of the bias issue, it's very hard to find data without bias, and in fact, just defining what bias is actually very tricky, because one person's bias is another person's, that's the way the world is, right? In many cases, and there can be legitimate disagreements about, what is the appropriate sort of bias. I think one place where AI can really help, though, is just in the same way that journalists will, if you go read a journalist's bio on, say, the New York Times or something, they'll try and describe what their bias is or kind of their philosophy. In the same way that there's no sort of unbiased journalist, there's going to be no unbiased sort of AI-generated policy, but at least AI could potentially help us in identifying what the bias is. Say, okay, not identifying, okay, this is the completely unbiased approach, but saying, okay, this is how we define bias, this is a precise measure, and this is how, and we're going to measure it in a way, sort of relatively precisely, so that it can be exposed. And then people can make their own decisions about, is that something I want to pay attention to, or how should I weight that? Does that address the question? Yeah. Mm-hmm.
This has been fascinating, so thank you very much. Recently, I was reading about a satellite launched by SpaceX, a collaboration of the Environmental Defense Fund and Google's AI-powered tools to monitor and identify methane emissions around the world, map them, identify the flows, the concentrations, et cetera. In light of what Professor Brett was talking about with NOAA data, are we taking the right steps so that information collected from private activities or public activities is something that will be reliable and trusted for policymakers, for decisions about what to do about the implications of all these things that you're talking about, that reliability of the data, trust of electorates around the world or policymakers?
So I don't know specifically about this collaboration, so I don't know what agreements they've come up with, but in general, for a long time, the best information about the environment was coming from governments, and it's a relatively new phenomenon that we're starting to get significant private sector data. And so I think that's very exciting that there are these partnerships that are collecting what we think of as kind of ambient environmental data that otherwise we wouldn't get. Typically, the private sector operations are like oil rigs or something that are collecting data about their operations specifically. And so we've had plenty of that data, but this kind of baseline monitoring happening by the private sector is very new and very exciting. And there have been, in general, especially with organizations like Google, there have been a lot of efforts to ensure that that data is linked in with existing standards for environmental data. So certainly larger enterprises like those ones have good integration. That being said, the source of the data is very important in how it's used in regulation and ensuring that it meets regulatory standards, whatever those are, and unfortunately they're slightly different for each regulation. So how data has to be structured and how trustworthy it has to be, how accurate it has to be is a little bit different under each environmental regulation. So it becomes tricky to keep up with all of those, and then it's much different if you then get into litigation, right, in court, where you're going to have even different standards. So that being said, I think in that case, because it is a large enterprise, I'm assuming that they've done pretty good work to link in what data they're collecting with existing management regimes, but I don't know specifically. I do know that there are other similar projects that are starting to be done. Ocean and autonomous vessels are some of them where there have been strong partnerships between NOAA and these private sector enterprises to be able to ensure that the data is being used. So I think now that these are, it's in some ways it's great that this is a relatively new area, because it means that this type of data production, the private sector type, is evolving at the same time as our new understanding of how we should be collecting data is also evolving. So it's not this historical ingrained approach that's a little bit out of touch with where we are. So I think there's much better collaboration happening now. But that's not always the case, right, with smaller sector, smaller scale private enterprises. So it's still quite varied. And I'm curious to look at this example now.
So it was an honor for me to be the moderator for this panel. You guys are brilliant. Thank you. I learned a lot from you. Thank you very much for being here. Thank you to the audience. So big round of applause for our panelists. Thank you very much, and may you have a great day. Thank you.